Swayam Prabha. Digital India. Educated India.
Let me start where I had left off last time. I was trying to tell you how useful the Pauli matrices were. We're going to do a little more of matrix analysis and properties of Pauli matrices and what fundamental role they play in this whole business. So if you recall, the three Pauli matrices are defined as sigma 1 is 0, 1, 1, 0. Sigma 2 is 0, minus I, 0. And sigma 3 is a diagonal matrix all the matrices are square equal to the identity matrix. So sigma I squared equal to I equal to 1, 2 or 3, doesn't matter. And then we also had the commutation relation, sigma j, sigma k is 2I epsilon jkl, sigma L, and we had sigma j, sigma k plus equal to 0 for j not equal to k. They anti-commute with each other, and the commutator is given by this third mid. Sigma 1, sigma 2 is 2I, sigma 3, and so on in cyclic permutation. Yes. We also pointed out a very important property, namely that any 2 by 2 matrix M, an arbitrary 2 by 2 matrix with complex entries, can be written uniquely in the form A naught I plus A dot sigma, where A is the components A1, A2, A3, and sigma is shorthand for a set of three matrices, sigma 1, sigma 2, sigma 3. So this is just a matter of notation. I should really write A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3. That's tedious to write, so I just write A dot sigma, making sigma look like a vector. It stands for this triplet of matrices. That's all, it's just a matter of notation. And then the question we posed was, what is e to the power I A dot sigma equal to? Since any 2 by 2 matrix can be written as a linear combination of the unit matrix and the sigma matrices, that is true even for this exponential. Even this should be writable in that form. So even this, the answer can be guessed. It should be something like I plus something dotted with sigma. Need not be the same vector A, but some other vector B maybe, dotted with sigma. So it's got to look like that. There's no choice. And I could also have a coefficient depending on the A's. So the answer must look like that, necessarily must look like that, no other choice. And the question is, what is it? For that, we use the property of anti-commutation, and we discovered that you can square this matrix very easily. So A dot sigma squared is equal to what? Is equal to A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3 whole squared. And that's equal to, there are three terms which are direct products, A1 sigma 1 the whole squared, but sigma 1 squared is the unit matrix, the identity matrix. So this is equal to A1 squared plus A2 squared plus A3 squared times the identity matrix plus A1 sigma 1, A2 sigma 2 plus A2 sigma 2, A1 sigma 1. That's the anti-commutator of sigma 1, sigma 2, so it vanishes. The cross terms vanish, so it's plus 0. Is that clear to everybody? A plus B the whole squared, if A and B are matrices, is A squared plus AB plus BA plus B squared. And in this case, AB plus BA turns out to be 0. A1, A2 are just numbers. So the anti-commutator helps you to do this. right away. And this can be written as A squared I. I define A squared to be A1 squared plus A2 squared plus A3 squared in the standard way in which the magnitude of squared is equal to the sum of the components squared. So this thing here immediately tells you that A dot sigma cube is equal to A dot sigma times the square. But the square is given by this. And the identity matrix doesn't do anything. It multiplies back and forth. So this is equal to A squared times the identity matrix, but that doesn't do anything. Therefore, what is A dot sigma to the power 4? Is A dot sigma times this, but A dot sigma squared is A squared times I. So you get another A squared and it becomes A to the power 4I. Therefore, e to the I A dot sigma is equal to, well, first you have the identity matrix 1 plus I A dot sigma over 1 factorial. That's the definition of the exponential. You expand in these powers, plus I squared A dot sigma, the whole squared, over 2 factorial, plus I cube A dot sigma cube over 3 factorial, plus let's do one more term, I4 plus dot dot forever. It's an infinite series. And what's the first term equal to? I plus, you can't do anything with this term. There's no further simplification. So it's I A dot sigma. This is when you should not be copying things down from the board. What should you be doing instead? What should you be doing instead? You should be watching me doing it and waiting for me to make a mistake, which I'll do occasionally deliberately. Okay? And then try to reproduce it on your own. Then you learn something. Otherwise, you become very efficient stenographers. But unfortunately, stenography is a talent which is no longer needed now that we have computers. So taking dictation is not a talent which is needed at all. On the other hand, understanding is needed completely. Right? And remember, you're going to have stiff competition because you're going to live in a world in which the machines are more intelligent than most people. Really. So take note. Yeah.
Sir, why do we need to have I in the exponential?
Why do I need to have? Why should I have an I here? I don't have to. But why did I put an I there? Right. I don't care, because if I don't have that, then I have cos hyperbolic theta plus sine hyperbolic theta. So I don't care.
Sir,
Why did I put an I there?
sir, is it to generalize the Euler's formula for complex numbers, for matrices?
Well, Euler's formula is a good question, but you see, the problem is that Euler's formula says e to the I theta is cos theta plus I sine theta. I agree. On the other hand, e to the theta is equal to cos hyperbolic theta plus sine hyperbolic theta. So it's the same formula written for an imaginary argument. I don't need the I, but I put the I there for a very specific purpose, because I don't need it. I can absorb it in A. I never said A has to be a real vector. A is just A1, A2, A3. I can absorb it in A, but you will see the use of putting an I here. It helps for the application I have in mind. So bear with me for the moment. It's no loss of generality to put an I there. Okay? We'll get to this. Yeah.
So from this, can we define the sign of a matrix, the cos of a matrix?
I'm not defining the sign of any matrix.
Can we do it from this?
No, I don't know what you mean by sine of a matrix or cosine of a matrix. How would you define the sign of a matrix? It's a valid question. How would you define it?
Sir, you could take e to the I.
Exactly. You
and
start
then
with the exponential map. You define the exponential of a matrix. Then the sign is very trivial, right? It follows from these formulas. Sine theta is equal to e to the I theta minus e to the minus I theta over 2i. So instead of I theta, if you put matrix M, sin M is defined as e to the I m minus e to the minus I m over 2i. So once you've defined the exponential of a matrix or an operator, you've defined everything connected with it. You've not defined log. That's a very tricky issue, the log of a matrix. I'm not going to do it here. It's a little bit more advanced. But apart from that, the exponential is treatable. So where does this leave us? The first term is this. And what's I squared? So it's minus a squared by 2 factorial. Because a dot sigma whole squared is a squared times the identity matrix, which I don't bother to write, or if you want, I'll write it here. Minus I a dot sigma a squared divided by 3 factorial. Because a dot sigma whole cubed, we already wrote it, I erased it, is a dot sigma there, sitting there, and then it's a squared times the identity matrix. The a squared is here. Okay. And then the next term is plus I power 4 is 1. This is a power 4 by I plus dot dot. So as I promised you, the answer is turning out to be a linear combination of the identity matrix and a dot sigma itself. A dot sigma appears in every alternate term and a identity matrix appears in every alternate term. So we have our final answer, which is e to the I a dot sigma is equal to I times, let's pick up coefficients of I. There is 1 here, 1 minus a squared by 2 factorial plus a4 by 4 factorial. No medals for guessing what's the next term. Dot dot dot, etc. And then plus I a dot sigma. The I comes out, and then inside the bracket there's a 1. And the next term is minus, there's a term minus a squared by 3 factorial plus a4 by 5 factorial dot dot dot. That's what it is. What do we do with this? What's this term? What's this equal to? Cosine of A. So we have a very nice formula which says I cos A where A stands for square root of A1 squared plus A2 squared plus A3 squared. It stands for that. And what do I do with this? Multiply and divide by A. So let's divide by A and multiply by A. So that's an A and makes this cubed and makes this 5 and so on. And what is this equal to? Sin A. So we have plus I plus I sin A by A dot C. That's the most you can do. The coefficient of I is cosine of A. The coefficient of A dot sigma is I sin A by A. When you derive a formula like this, you should check. You should always check that you have not made any mistakes. You should check very carefully for various limits. What happens if the vector A is 0? What happens if A1, A2, A3 are all 0? What's the left-hand side? Just one, or the identity matrix. Everything is a matrix. So just the identity matrix. What do you get here if you put A equal to 0? This becomes I. What happens to this? This becomes 0, but what happens to this? You have to take the limit. What's sin A by A as A tends to 0? Tends to 1. So you're all happy. This tends to 1, this tends to 0, so the product is 0, and you get back to identity matrix. Okay? So that's a check on your calculation. Now, a quick word as to, before we go on to the next one, a quick word as to why there was this I. Are you familiar with, you're familiar with the property that sigma, each sigma matrix, sigma I dagger is sigma I. It's Hermitian. It's equal to its own complex conjugate transpose. Okay? Are you familiar with the idea of a unitary matrix? A unitary matrix is one where U dagger is equal to the identity matrix. Or U dagger is not U, but U inverse. So e to the I times a Hermitian matrix is a unitary matrix. Because if I took the dagger of this guy, I'm going to get a minus here, and this is, it remains as it is, A dot sigma. And if I multiply e to the m by e to the minus m, I get I. So the exponential in this form with this I gives you a unitary matrix. And in quantum mechanics, we use unitary operators all the time for physical operators, because the unitary operator ensures that because it's unitary, probability is conserved. It has to do with the lack of dissipation, finally. That's the reason for traditionally putting an I here. I'll come back to this. I'll come back to how this represents a rotation matrix. But meanwhile, let's play with this a little bit more. Let's look at another matrix, not a sigma matrix, a more general matrix, and see whether we can find its exponential. The question you could ask is, I found the exponential of a 2 by 2 matrix, arbitrary 2 by 2 matrix, because this is really arbitrary completely. Can I find the exponential of an arbitrary n by n matrix? And the answer is no. There's no simple formula like this. There's no equivalent of the Pauli matrices in higher dimensions, except in very special cases. If you tell me a very special class of matrices, I may be able to exponentiate it. But otherwise, it's a mess. You just have to multiply repeatedly. Let's look at this matrix. Let's look at an n by n matrix. M defined as 1, 1, 1, 1, 1. All elements are equal to 1. I could look at a more general case where all elements are equal to some number and then take out that number. It doesn't matter. But the simplest case is when everything is equal to 1. What are the eigenvalues of this matrix? First of all, is it Hermitian? It's equal to its own conjugate transpose, because there's nothing to complex conjugate here. And clearly, M is a Hermitian matrix. Okay. What are the eigenvalues? How will you find the eigenvalues? Well, let's take a simple case, find it, and then see if we can generalize this. If M is a 2 by 2 matrix, 1, 1, 1, 1, what is M squared? What are the elements of M squared? 2, 2, 2. It's equal to 2m. We can find the eigenvalues by writing determinant lambda I minus m is equal to the determinant of lambda minus 1, minus 1, minus 1, lambda minus 1. What's the value of this determinant? Equal to lambda minus 1 whole squared. If I put it equal to 0, which is the condition for the eigenvalues, what are the eigenvalues? One eigenvalue is 2 and the another eigenvalue is 0. That's the solution of the secular equation. What do you think will happen if I take M equal to a 3 by 3 matrix? What is M squared? 3, 3, 3. So what's the general pattern? M squared is n times n. What do you think are the eigenvalues of this matrix? N and 0, but it must have capital N eigenvalues. It's an n by n matrix. You have to tell me, In general, it satisfies the determinant lambda I minus m equal to 0. You have to do that for the n by n matrix, which is not trivial, but it's not so hard. You can play around with that determinant a little bit. After all, what will you get? You get determinant lambda minus 1, minus 1, minus 1, way to minus 1, minus 1, lambda minus 1, minus 1, all the way, minus 1, etc. You have to simplify this, and the simplest way to do this is to ensure that you get zeros in one row at least, except one element. And then the whole thing will repeat itself in pattern, etc. Right? But you see, there is a theorem in matrix analysis which says the following. It's called the Cayley-Hamilton theorem, which helps you to solve this problem by inspection. The eigenvalue equation, determinant lambda I minus m equal to 0, is called the characteristic equation. So you take a matrix M, square matrix, you write down this determinant condition for the eigenvalues. That equation is called the secular equation or characteristic equation. And there's a theorem in matrix analysis which says, it's called the Cayley-Hamilton theorem, very useful theorem. And it says something apparently very simple, but not so trivial. It says every matrix, n by n square matrix, every square matrix satisfies its own characteristic equation as a matrix. This is not a trivial statement, because if you took an n by n matrix and I wrote this equation out, determinant equal to this thing, what sort of equation is it? The unknown variable is lambda and it must have capital N roots. What sort of equation is it? What is the leading power? N itself. So this equation will be of the form some a naught lambda to the power n plus a1 lambda to the n minus 1 plus dot 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 plus a n times I equal to 0. Guaranteed. It's a polynomial equation of order n. That's why its roots, there are n roots. Okay. That's the characteristic equation. In terms of the eigenvalues, by the way, I can divide by this. So let me just divide by it and have it in this form. It's an nth order equation, no doubt about it. So I can take the coefficient to be 1. Okay. What is a1 then in terms of the roots? Minus the sum of the roots. What is a2? Product 2 at a time with a plus sign. Then what is the next term? 3 at a time taken with a minus sign, and so on, right? So the eigenvalues are determined by these coefficients. This is the characteristic equation. What does it mean to say that every matrix satisfies its own characteristic equation? It means that it implies, the Cayley-Hamilton theorem implies that m to the n plus a1, m to the n minus 1 plus dot 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 plus a n I equal to 0. So where lambda appears, you replace it by the matrix itself, and that equation is guaranteed to be satisfied. It's not a very hard theorem to prove, but it looks trivial, but it's not. So it's saying something profound. It's saying that this ordinary algebraic equation, if you took the unknown lambda and replaced it by the matrix itself, the equation is satisfied. Which means that for every n by n matrix, you can write m to the power n in terms of the lower powers. You can always do that. And the characteristic equation is guaranteed to be of order n. Can we find the characteristic equation of this matrix in which all the elements are 1? M squared equal to nm, but that's not the characteristic equation because it must be an nth order equation. What should I do? What is m cubed? What is m to the power n? And what's the order of this equation in m? N, order n, polynomial equation. If I bring it to the left hand side, this is equal to 0. That's an nth order equation satisfied by this matrix M, this very special matrix. But we know that the characteristic equation of this matrix must be the nth order equation. So this is the characteristic equation of the matrix. Now I apply the Cayley-Hamilton theorem in reverse. Whatever equation was satisfied by lambda is satisfied by m. So I've got an equation with m here. So what do I get? So check this out. Check this out for the 3 by 3 case. 2 by 2 is very trivial. We already checked it out. 3 by 3 case, check it out. So let me write the answer down for this matrix. M has eigenvalues lambda 1 equal to n, lambda 2 equal to lambda 3, equal to 0. All the eigenvalues of this matrix except one of them are equal to 0. And one of them has eigenvalue n. What is the eigenvector corresponding to this eigenvalue n? What do you think is the eigenvector? We can do that by inspection because you're saying 1, 1, 1. Acting on an eigenvector is equal to n times the same eigenvector. Can you guess what this eigenvector is? You need an n here. Now this is simple guesswork. What should this column vector be so that you get an n times the same column vector? Yeah?
Will all the elements be n?
Pardon me?
Will all the elements be n in the column?
Do they have to be n? Actually, the elements are determined only up to a multiplicative constant. That's quite true. The gist of what you're saying is, will all the elements be equal? You can take out a common factor, right? Will they all be equal? And what's the simplest one that you can write? 0 will finish off everything, right? It's not 0. 0 will give you 0 here, but you've got to have n here. So what's the guess? 1. Yeah, 1. It's called a uniform eigenvector.
In the previous statement, won't it be a1 equal to n and not lambda 1? That you, like because
Yeah, a1 is also equal to n with a minus sign.
No, but
because all the other eigenvalues are 0.
No, not this one. But the characteristic equation isn't the coefficient equal to n and not the
Here?
yeah. So a1 is n, right? But then you wrote lambda 1 on the.
In general, no, I'm jumping back and forth between these two. The general characteristic equation is this: all the lower order terms will be present. Okay, the eigenvalues are not all equal in general for an arbitrary matrix. The first coefficient is minus the sum of the eigenvalues. That there's no doubt about. This is the eigenvalue equation. The roots of this equation are lambda 1, lambda 2 up to lambda n in general complex numbers. Then you're guaranteed that m satisfies the same equation with the same coefficients. Can we find the exponential of m? We found its eigenvalues. We found one of the eigenvectors. We need to find the other eigenvectors in which you have zeros here. 0 here. So it must be an eigenvector such that if m acts on it, it goes to 0, the null matrix. That's a less trivial thing to do, but it's not very hard. You try it out for the 3 by 3 case and then you see the pattern, you generalize it. Can we find the exponential of this m? We start with the observation that m is n times n. Therefore, m squared equal to n m squared equal to n squared times n. M cubed equal to n squared times m. Etc. So what's e to the power m? Summation n equal to 0 to infinity my m to the power n over n factorial is equal to I. Yeah, 1 second. Yeah.
Won't f square be n squared f squared?
Sorry. Sorry, you're right. Nm squared. M squared is nm squared. Sorry, what did I do? We start with m squared is nm. That's it. Okay, thank you. That's equal to I plus m by 1 factorial plus m squared by 2 factorial, but m squared is nm. Can you sum this series? Take out the m constant and take out the m. What do I do next? No, e power n will not have this, right? We'll have x squared by 2 factorial x cubed by 2. Multiply and divide by n, so m over n, etc. And then what? What is this guy? E power. The job is done. That's the closed form. So the exponential of m in this problem happens to be a linear combination of the matrix and the identity matrix. The coefficient of the matrix is e power n minus 1 over n. Okay. There are very few matrices which you can actually exponentiate like this, but this is one of them. Now let's get back to our e to the I a dot sigma, and let me show you where this I comes from. Let's do it in 2 dimensions because then I can draw a picture and it's very trivial. So if I took 2-dimensional coordinates x and y, and I rotated the coordinate system by some angle alpha to get x prime and y prime, then I have x prime, y prime equal to a rotation matrix parameterized by alpha x, y. And what's R of alpha equal to? I'm going to do a little bit of reverse engineering here because we already know the formula from trigonometry for a finite rotation. Generally you don't, in general in n dimensions, but in 2 dimensions we know the answer from elementary trigonometry. So I'm going to work backwards and ask what happens if I take the following attitude. I take the attitude that to get to a coordinate system like this, I first rotate by delta alpha, then by another delta alpha, then by another delta alpha. I go on adding these delta alphas and rotating by infinitesimal amounts till I reach the alpha. So what is R of delta alpha? If this is R of alpha, and alpha is now an infinitesimal delta alpha, to first order in delta alpha, what is R of delta alpha? No, what I'm going to do, my strategy is going to be the following. I'm going to multiply by n I'm going to make this smaller and smaller, this larger and larger, such that the product gives me a finite rotation. I'll take the limit. So what is R of delta alpha from this equation? If I want to, it's cos delta alpha minus sin delta alpha, sin delta alpha, cos delta alpha. But I want to first order in delta alpha. What is cos x to first order in x? What's the series for cos x? 1 minus? The next term is x squared, it's second order in delta alpha. So what's the series? What's the cos alpha to first order in delta alpha? 1. What's sin alpha? What is sin x to first order in x? X or minus x? Sin x. X, very good. So this is delta alpha minus delta alpha. Sin alpha here is delta alpha. And this is 1. That's the rotation matrix for an infinitesimal rotation delta alpha, correct to first order in delta alpha. But that's the sum of two matrices. So this can be written as the sum of 1, 0, 0, 1 minus delta alpha times 0 minus 1, sorry. So that's equal to I, right? So R of delta alpha is equal to I plus delta alpha times this matrix 0 minus 1, 1, 0. Does it look like a Pauli matrix? Which one does it look like? Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I 0. You're asking my permission to do it, or you're going to do it? Why not? It's a free country. So what should I do to get a sigma 2 there? Divide by I. So take out an I, and then you get a 0 minus I 0 with a minus sign. You're saying divide by I write it as minus I on top. If I multiply these two, you get a minus 1, which is what you should get. If I multiply these two, I get a plus 1. So what's this matrix equal to? These are all numbers. Times what's this matrix? Sigma 2. Okay. Agreed? What do I do next? Well, I argue now that I come back to this matrix. R of alpha is equal to R of delta alpha, R of delta alpha, dot, 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 n factors. Yeah.
Sir, why did you take it to first order?
Why did I take it to first order? Because there was this grand old man called Newton who said in calculus, keep infinitesimals to first order, throw out higher order infinitesimals and take the limit.
Okay. Oh, that's why you're taking it as small as possible.
Yeah, it's an infinitesimal. I'm going to get a differentiable function of this alpha, which you already know, it's cos alpha, sin alpha, etc. Okay. So this is the way you do it, by the way. You always split the problem into smaller problems which you can solve, and let me give you another example as soon as I finish this. Okay. What is this equal to? What is R of delta alpha? Oh, by the way, R of alpha equal to limit n tends to infinity. This guy such that n delta alpha equal to alpha. I'm going to take the limit. So this is equal to limit n tends to infinity. What is r of delta alpha, by the way? It's I minus that guy, right? To the power n. I have to raise it to the power n. It's the same matrix repeatedly applying delta alpha each time. So this is a delta alpha. Each of these is delta alpha, and finally it builds up alpha in the limit. What do I do next? There's a very small quantity here, and there's a very large quantity here. So I should take the limit such that the product of the two is finite. Since n delta alpha is alpha divided by n. So I can replace this by alpha divided by n. What is limit n tends to infinity 1 minus x over n to the power n? What is limit 1 minus 1 over n to the power n? Yeah? E, it's E. If I put a plus, it's E. If I put a minus, 1 over E. So if you generalize this, 1 plus x over n, what's that equal to? E power minus x. That's one definition of e power minus x. What happens here? The fact that one of the terms is a matrix doesn't matter. The exponential function is still defined. So in analogy with that, what's this equal to? So we found that r of alpha equal to e power minus I alpha. If you now go back and do forward engineering and write sigma 2 squared is I, sigma 2 cubed is sigma 2, etc., you will discover that this formula is also equal to cos alpha minus sin alpha, cos alpha. We already know that. We started with that and we worked it out our way to this. This is the more general form. When you have three-dimensional rotations, this is the more general form. But how many such? This is called the generator of infinitesimal rotations in 2 dimensions. Because its powers generate these rotations. And it's called an infinitesimal generator, or more properly, a generator of infinitesimal rotations, because you build up a finite rotation by a sequence of infinitesimal rotations. Now, several lessons come out. You see the power of this I here. You see the reason for the I here. So that this whole operator is unitary. Okay. This is the traditional standard way in which rotation matrices are written. This is a special case in 2 dimensions. When you have 3 dimensions, it gets harder, because how many axes are there to rotate about in 3 dimensions? 3. So there are 3 generators. Actually, a definition of a rotation is a little more complicated. In n dimensions, there are n into n minus 1 over 2 generators. And if you solve the equation n times n minus 1 over 2 equal to n itself, the only positive integer solution is 3. So 3 dimensions, you have 3 orthogonal planes and 3 axes. But in 4 dimensions, suppose you are looking at x1, x2, x3, x4, you have 6 possible planes. x1, x2, x1, x3, x1, x4, and so on. So you really have 6 generators. And this formula will get incredibly more complicated. There are 6 possible generators of solutions of rotations and so on. Pardon me? Hmm? Will that be? If you make x4 equal to I times t, it will become the same thing. It's very closely related to Lorentz transformations, not quite. Okay, Lorentz transformations are like pseudo-rotations, because time is not treated on the same footing. What's important here is the use of this formula, the exponential formula, and then you get a generator of rotations in this form. There are many ways of writing rotations in 3 dimensions. One way would be to say, I prescribe to you a sequence of operations by which a general rotation can be obtained in 3 dimensions. So if you start with some x, y, z like this, I will always use a right-handed coordinate system, so that if I rotate from x to y like a screwdriver right-handed screw, it goes up along the z direction, this fashion. So in general, this is rotated by rotating about the z-axis, which will change the x and y axis to x prime, y prime. Then you rotate about the x prime axis, which will change the z and y prime, and then you rotate again about the x-axis, about the z-axis. So there are many, many conventions possible. There are 12 different conventions possible for defining a rotation in 3 dimensions, a sequence of 3 operations. Each of them is represented by the exponential of I times some infinitesimal generator times the parameter. But the one that's most physical is the following. You can take any rotation in 3 dimensions and say, I'm going to rotate about this unit vector. So some direction in space, and I'm going to rotate about that unit vector. And I rotate by an amount psi, angle psi, and that can be anywhere from 0 to 2 pi. So about this vector, this is the plane perpendicular to this vector, you rotate from the initial position to psi through an angle psi. Then it turns out that the rotation about this unit vector through an angle psi can be written as e to the power I, always e to the power I or minus I depending on your convention, times psi times n dot, the generator J of rotations. This is the shorthand for 3 matrices J1, J2, J3, called the generator of rotations or the angular momentum, and it's given by 3 by 3 matrices of a certain kind, similar to the Pauli matrices in 2 by 2, in the 2 by 2 case. So that's a general way of writing a rotation in space. Yeah. And then there are properties of this parameter space which you can study and so on. Yeah.
Sir, so as long as n cap is not a n cap is an n-dimensional vector and J has n different matrices.
No, this is only true in 3 dimensions.
Oh yeah.
In 4 and higher dimensions, or even in 2 dimensions for that matter, rotating about an axis is not essential. Because suppose I imagine for a moment I'm in 4-dimensional space, x1, x2, x3, x4. I make a transformation which is linear, homogeneous, and about retains the origin in the x1, x2 plane. It leaves x3 and x4 unchanged. So which axis have you rotated about? There's no need for such an axis at all. Okay. Even in an odd number of dimensions, you can always identify an axis of rotation for every rotation. But in an even dimensional space, it doesn't have to be so. There could be rotations without an axis of rotation, but a plane, rotation in a plane. So rotation matrices are very intricate properties and very interesting properties, and they're studied in group theory and quantum mechanics and so on. So we will not get into that. Any other questions? Yeah.
Sir, what exactly is J over there?
If you remember what Professor Lakshmibala said, she said that you have a spin operator such that Sx comma xy is IH cross times Sz and so on, right? And cyclic permutations. And she called this the spin algebra, right? It's more correctly called the angular momentum algebra. So now, including orbital angular momentum, spin, which is an intrinsic angular momentum, or any kind of angular momentum whatsoever, in 3 dimensions, the rotations are specified by 3 operators, J1, J2, J3, which will generate rotations about the 1, 2, 3 axis respectively. And they satisfy this condition Ji, J subscript J, Jk equal to IH cross epsilon JKL, JL. forms what's called the closed angular momentum algebra. There are 3 such relations. And that's the definition of the high angular momentum. Any angular momentum operators will satisfy that in 3 dimensions. It's exactly the same as this. So it doesn't matter whether this J, I didn't want to represent it by capital S because it could be angular momentum of the orbital kind. So to generalize it completely, or a combination of the two, to generalize it, one uses the symbol capital J for angular momentum. That's what it is. One can generalize this to n dimensions in the n-dimensional rotation. It's a little more intricate than this, and let me write it down for you so that this is outside the framework of what we are saying, but let me write it down for you. Rotations in n dimensions might as well write it down because it's not very hard to understand the structure of it. Rotations in n dimensions are given by a set of generators J labeled by indices J and K, J, K equal to 1, 2 up to n, satisfying the following algebra. This is a tensor of rank 2 and it's antisymmetric. How many components does it have? It's in n dimensions, a tensor of rank 2. So you write it down as a matrix, for example, it will have n squared elements. Yeah. But remember, it's an antisymmetric tensor. So all the diagonal elements are 0, and the off-diagonal elements above the principal diagonal are minus the ones below. So there are n times n minus 1 over 2 independent elements. Okay? In 3 dimensions, it would be 3 elements. In 4 dimensions, it would be 6 elements, and so on. Okay. And they satisfy the following algebra. In quantum mechanics, they would satisfy Jk, J, Ln equal to IH cross times the following quantity. J, L times the Kronecker delta Kn plus J, Kn times the Kronecker delta Jl minus Jn Kronecker delta Kl. It looks formidable, but it's not really. Just a combination of that kind. That's your angular momentum algebra in n spatial dimensions. It has a very characteristic structure of this kind. You form an algebra as soon as the commutator of these operators is a linear combination of such operators. It's called a Lie algebra then, under suitable circumstances. So this is what the angular momentum algebra looks like in n dimensions, where n is arbitrary. Now, I don't know if any of these people introduced the metric. Right in the beginning, Professor Ghanshyam Date introduced the concept of a metric and curved space and so on. If you had relativity and if you had general relativity with a definite metric in space, curved space and so on, then these deltas get replaced by the metric tensor. That's all that happens. Okay. If I use the metric tensor here, I could write down the relation for Lorentz transformations. All Lorentz transformations, including boosts as well as rotations. They all follow from similar algebras. So the point that I want to summarize is there's a general structure to this whole business which will handle all sorts of physical transformations in a unified manner. And that's got to do with the algebra of the generators. Yeah. Yeah.
Sir, related to this, but not exactly related to this. Other than things like sets, other than like collections, is there anything which is any mathematical object which is not a tensor?
Which is not a?
Tensor.
Hardly any mathematical object is a tensor. Why do you say that? A matrix is not a tensor. All matrices don't have to be written as tensors. You could write it in that form, but the tensor refers to a specific transformation property. A matrix is a different structure altogether. You may sometimes be able to represent tensors of rank 2 by matrices, but how will you represent a tensor of rank 3? So they are very different objects. What is common, what is useful to know is that in addition to, are you familiar with what a group is? The postulates of what a group is? We are sort of skirting around the idea of groups. You've skirted around Lorentz groups, you've skirted around the group of general coordinate transformations, the group of rotations, the group of the spin group, and so on and so forth, without specifically being told so. But the following has a very useful structure. You could ask, why do these commutators appear all the time? And the answer lies in what is called a Lie algebra. So let me explain what a Lie algebra is. It's a very general mathematical structure which appears in many, many instances, and I will give a couple of examples. It consists of a set of elements which, for want of a better symbol, let me call it elements. I'll call these elements alpha, beta, gamma, etc., etc., in which a composition law is defined. Some composition law, which is denoted by this, alpha composed with B on this side. This composition has the property that it produces here on this side a linear combination of similar elements. So this composition law has got a weird property. It produces, when you compose two elements, it produces one more element from the set. Okay. It also has the property that alpha composed with beta is minus beta composed with alpha. So it's got this anti-symmetry property. And then it's associative. So the composition of the usual associative, etc., axioms. But the more interesting point is the following. Alpha composed with beta composed with gamma plus cyclic permutations is equal to 0. So gamma composed with alpha composed with beta, and the third one in cyclic permutation gives you 0. No, alpha composed with beta gives you another, not some necessarily sum of overall elements, some linear combination of elements. Could be just one, could be two, could be three, could be many more, etc. Just a linear combination. Pardon me? It depends on the algebra. Now you're all familiar with one example, in fact 2 examples of a Lie algebra, which is, by the way, this set of postulates, plus a couple more technicalities, but essentially this. But you're all familiar with one such possibility. What is that? If you take n by n matrices, and I define the composition law to be the commutator in this fashion, that's my composition law. Okay. Then these postulates are satisfied. Do you agree that A commutator B is minus B commutator A? Do you agree that this is true? A commutator of B.
Sir, but how is, sir?
Yeah.
But how is like in matrices, like how is our commutator sum of linear combination of all other elements?
It's a matrix. It's not a linear combination of all of that. I wrote this very loosely to say there are more objects of that kind from the same element set.
Oh, okay.
That's all.
Okay.
All I meant to say was I didn't say they're linear or anything like that. Just more elements of the same set.
Okay.
0 because of the antisymmetry. These are abstract elements. Whatever be the nature of the elements, whatever be the nature of the composition law that I prescribe, it is antisymmetric. That's all that's needed. And by the way, this is called the Jacobi identity. So tell me, when you have square matrices of the same order, some fixed n by n matrices, n by n order, is it not true that the commutator is antisymmetric? So this postulate is satisfied. This postulate also is satisfied because you can verify that this is explicitly 0. So matrices under the operation of commutation form a Lie algebra. That's why this keeps appearing. But there is an even simpler example which you are familiar with. Can you think of it? A much simpler example of a Lie algebra. Are you going to define multiplication as well, or just addition, or what? What happens if I take three-dimensional vectors, ordinary 3D vectors which you are familiar with, and define the composition law to be the cross product? So is this not true? First of all, if A and B are three-dimensional vectors, isn't A cross B a three-dimensional vector also? So it belongs to the same set. If I define the composition law to be the cross product, is this not true? Is this not true also? A cross B cross C plus cyclic permutation equal to 0. Is that true or not?
Yes, sir.
Right? So ordinary three-dimensional vectors in 3D Euclidean space under the composition laws defined by cross product form a Lie algebra. Simplest example. The second simplest example is matrices of a given order, square matrices under the operation of commutation form a Lie algebra. Now it turns out that the generators of groups of transformations in physics that you are interested in always form a Lie algebra. And the Lie algebra has names on it, various names for it. For instance, if you took three-dimensional rotations, the three angular momentum operators form a Lie algebra. And there's a symbol for it. The rotations themselves are represented by orthogonal matrices. So you put an O, it's in 3 dimensions, so you put a 3, and it's got determinant plus 1, it's called a special orthogonal transformation. And the group this is read as SO3, stands for the rotation group in 3 dimensions. It has 3 generators which form a Lie algebra, and that Lie algebra is written by small letters instead of the big letters. What about rotations in a plane in 2 dimensions? How many generators are there?
One.
Just one generator. So there's no need for a Lie algebra. It's too trivial. There's no question of an algebra at all. SO2 is a very simple group, a very trivial kind of group in a certain sense. How would you denote, just a matter of notation, how would you denote Lorentz transformations in this notation? They're given by pseudo-orthogonal transformations, which are also orthogonal, in 3 space and 1 time dimension, and it's written like this, SO3, 1. It stands for the Lorentz group, boosts as well as rotations, and it's got 6 generators. That's it. 3 of them are angular momentum generators and 3 are called boost generators. So the whole structure of this transformation theory is to try to generalize as much as possible and bring as many transformations into a common picture, as a common fold as possible. That's the idea. And the math you need for it is the theory of Lie groups and Lie algebras, which is why group theory plays a fundamental role in physics, modern physics.
Sir, can you like explain why Lorentz transformation is SO3, 1?
Because the time dimension
One is always included in transformations.
Pardon me?
Sir, like time is always included in transformations. That's why.
Yeah, we know after Einstein's discovery of space-time that space and time is one continuum. It's a space-time continuum. That the real invariance is under Lorentz transformations from one inertial frame to another, as well as spatial rotations. But the space dimensions are treated differently from the time dimension, because remember that interval that Date talked about has got a minus sign. It's c squared t squared minus r squared, that
Yes.
minus sign. So the t and the r is separate, are treated differently altogether. They have to be. And to keep track of that, you put a minus.
So instead of SO4, we are writing SO3,
Yeah, so what
1.
happens is the following. He's got a good point here, which I should have mentioned. If a matrix is a pure rotation, then R transpose is equal to the identity matrix. But if it's a Lorentz transformation, this is not true. Let me denote a Lorentz transformation in 3 plus 1 dimensions by capital lambda. Then this is not true. This is in 3 dimensions. This is in 4 dimensions. It is not true that it's equal to the identity transformation. So it's not orthogonal. Instead, what happens is lambda G, lambda transpose is equal to the metric matrix G, little g, where this G stands for something that he already introduced. It stands for 1, 0, 0. Very good, stands for this. So it's not orthogonal, it's almost orthogonal. It's called pseudo-orthogonal. And to keep track of that fact, you don't write this as SO3 or SO4, but SO3, 1. SO4 would look exactly like SO3 with 6 generators. Nothing interesting. Again, an orthogonal transformation.
Sir,
But Lorentz transformations are not.
Lambda G lambda transpose is equal to G. Like one of the solutions could be lambda transpose is equal
Yeah,
to.
so this lambda is, it's a good point. What does this lambda look like? Well, with our convention, this lambda would look like this. 4 by 4 matrix, in which this is the first row and first column here. This is purely spatial. The index running over 1, 2, 3, and this runs over 0, 1, 2, 3, etc. 1, 0, 2, 0, and 3, 0 out here. So these generators, this lambda would look like this, and if you had a Lorentz transformation, it would only affect time and one space dimension and not the other 2 space dimensions. So rotation would involve only the spatial coordinates, but the boost would involve the direction of the boost is one of the axes and the time axis. It would mix up. Both those are included in this lambda matrix here. Okay. I could still write it very much looking like a rotation in space and time, in space-time, but it would not involve the rapidity variable.
Sir, one more doubt, sir. How do we make sure that lambda transpose is equal to I is not included in the solutions of these? Because one of the solutions of lambda G lambda transpose is equal to G has lambda transpose equal to I.
Yeah, so this is incredibly complicated. In general, it's a mixture of boosts and rotations. About rotation about an arbitrary axis in space, boost about an arbitrary direction in space, and so on.
So when we include G, we by ourselves.
So, but you're guaranteed, no matter how complicated it is, you're guaranteed that if it's a Lorentz transformation, it would satisfy this equation from the very structure of the transformation. The interesting thing is, if you take a velocity, a boost in the x direction, say, and you follow it up with a boost again in the x direction, the resultant is a boost in the x direction with a specific addition law for velocities, v1 plus v2 over 1 plus v1 v2. If you take a rotation about any axis and rotate about any other axis, the result is a net rotation about a third axis of some kind. But if you take a boost in some direction and a boost in another direction, the resultant is not a boost in a resultant direction. It's a boost followed by a rotation. So the rotation gets mixed up with the boost. The boosts themselves don't form a subgroup. You would have heard of this phenomenon called length contraction along with time dilation. It took till 1957, as long as that, 1905 relativity, special relativity came in. But it took till 1957 before it was pointed out that the fact that two boosts in different directions will give you a boost and a rotation will geometrically distort the appearance of an object which is moving past you in such a way that you cannot directly verify length contraction. It would not show up as length contraction at all. You can directly experimentally verify time dilation, but not length contraction because of this geometrical effect, which was overlooked for many decades before it was rediscovered, if you like. Okay. If you go to YouTube, I don't remember the name of the channel now, you can get pictures of how the world would look if you're traveling at the speed, half the speed of light, for instance. What would things look like? There'd be so much distortion, spatial distortion, it looks nothing like what you're used to. For instance, if you enter a crystal, if you pretend you're a very small, tiny guy entering a crystal in which atoms are in a regular array, the crystal would look really distorted, bloated up, etc. as you get into it, approach it. So it would not look like a cubic lattice at all, but very different. If you fly past a bunch of skyscrapers, the skyscraper will turn around and show you the rear end which you have just passed. So there are weird geometrical distortion effects, and some movies exploit this and they calculate exactly what happens and so on. Just like the movie Interstellar. How many of you have seen this movie? Right. So all the trajectories that they show in this movie, the light paths, the distortion effects, etc., are mathematically correct. They're absolutely genuine. That's exactly how it would be if you could go to that place. Okay. So they were actually calculated by Kip Thorne, who's a Nobel laureate in physics and was the scientific consultant to the movie makers, etc. So in the same way, there are these YouTube picture clips of relativistic effects worth taking a look. By the way, the speed of light is fundamental. It cannot be exceeded. What happens if light is in water? The speed of light is less. Can you exceed that light? Can you exceed that speed? If you are in a vacuum, you cannot exceed the speed of light in vacuum, little c. But if you are in a medium, like water, can any object exceed the speed of light in that medium? That's not what the postulate of relativity says. You can very well exceed the speed of light inside a medium. There's nothing fundamental about the speed of light in any given medium. It depends on the medium. The only fundamental velocity is the one in vacuum, which cannot be exceeded. So inside a medium, you can exceed it. What happens if you took an object in the atmosphere and it exceeded the speed of sound? What does it lead to? It leads to shock waves. There's a shock wave cone and so on. And the sound comes out in a shock wave, right? In exactly the same way, if you have an electron traveling at a speed of light, at a speed greater than the speed of light in a transparent medium, like a swimming pool, for instance, or a piece of glass, then it emits radiation, and it's called Cherenkov radiation. And it would see a shock wave, because there's nothing fundamental about the speed of light in a material medium.
Sir, when you say speed of light in a medium, you say the effective speed of light?
Yeah, it's always the effective speed of light. C divided by, good question. C divided by. What symbol do you use for the refractive index? Mu. That's the speed. Mu is greater than 1. No, in between collision events and scattering and absorption events, the light is traveling at the speed of light in a vacuum. You can't beat that speed. However, the effective speed of light is diminished by this, the average speed. And you can exceed that. Charged particles routinely do that. When you look at accelerators and you look at what happens, you pass through a transparent medium, very high density, energetic electrons, for instance, they would emit light, which is a bluish light. It's called Cherenkov radiation. There is nothing which violates relativity.